So let's think of a couple of things. Well, we know that if we had a binary search, right, we could find the insertion location in log n time. The problem with that is even if we find the insertion location in log n time, inserting a value into a list, depending on, on average, inserting a value into a list, assume that you're always, on average, you're always going to insert in the middle of the list. Well, you have to move everybody else down one. So you find where you need to insert, you move everybody else down to make a hole, and then you insert the thing in. So even if we use the binary search to find where to put our value, right, like insertion sort, we're kind of moving our hole as we go. Otherwise, we would have to do it in a separate step, and we wouldn't actually save any time. So this inner loop here, right, where we're moving our hole, we have to do that even if we have something up here to tell us where to put the value in log n time. So this moving the hole is actually what takes the time. We could make our decision in log n time, but we couldn't actually put it in place in log n time. So we got to do better. And we know that anything that's going to do better can't scan the entire list. I'm thinking we're not going to get through. What do the exercises say here? Take a quick look at the exercises just for a minute. Awesome. Okay. If I get through this next topic, you guys are okay for the exercises. Aren't you happy? Okay. So we're going to build something called a merge sort. And at the heart of a merge sort is this concept of merging two sorted lists. So the cool thing about merging two sorted lists is that if you have two sorted lists, you can put all the items in those sorted lists into order in order of n time, where n is the length of the combined lists. So if you have 8 and 8, you can do it in 16 steps. If L1 is 8 things long and L2 is 8 things long, then you can actually merge things together in one pass, right? It's not an order of n squared algorithm. You can just pull them together really quickly. So at the heart of merge sort is this concept of quickly doubling the size. And by the way, that doubles the size of your list. So of quickly doubling the size of your list and maintaining a sorted order. So if we have L1 is 9, 12, 17, 25, and L2 is 3, 5, 11, 13, 16, what we want to do in a single pass is build the list 3, 5, 9, 11, 12, 13, 16, 17, 25, which are the combined elements of these in sorted order. Okay? So the concept on this is pretty simple. I'm going to go over for just another quick run to my handy dandy whiteboard. Okay, so let's take a look at what we want to do. Right? And we want to make this very efficient. So we're going to say L1 equals 9, 12, 17, and 25. Right? And L2 equals 3, 5, 11, 13, 16, 17, and 25. No, 13, oh man. 3, 5, 11, 13, 16, 17, and 25 come from the other list. Okay? And we want to merge these together into big L. So let's see how to do that. Well, we know that these are in sorted order. So if we want big L to be in sorted order, we know that the smallest value in L2 has to be at the front of L2, and the smallest value of L1 has to be at the front of L1. So we'll set up a little counter. I1 equals 0, I2 equals 0, and that will be the index of the smallest unused value in list L1 or L2. So we come in here, all we have to do is compare the front of the L2 queue to the front of the L1 queue, and whichever one is smallest is actually the smallest in both lists. So we come down here, we say, okay, I2 is pointing to the front of L2, that's 3, 3 is less than 9, 3 goes in this list, and now we're done with 3. Now we don't want to remove 3 because removing things from lists costs time and money, so we'll just move our index down 1. Right? And now the figurative front of our queue, our L2 list, is now at 5. 5 is less than 9. So with one comparison, we can build that out. Right? Move it down again. 9 is less than 11, so we pull 9 down here. We move the L1 pointer. 11 is less than 12. We move our pointer down. 12 is less than 13. We move our pointer down. 13 is less than 17. We move our pointer down. 16 is less than 25. And now L2 is exhausted. There's nothing left in L2 to be checked. So now we just say copy whatever's left out of L2 and pop it on the end. And that's really all the merge algorithm is. It's a really simple way of walking through lists and relies on the fact that the two inputs to the function are actually in order. So let's quickly write ourselves a little merge function. Right, we've got that down here in Spider. I1 is going to be our index for list 1, right? I1 is the index for list 1. I2 is the index for list 2. And our big L is just going to be the empty list to begin with. And I think we just... yeah, we're just going to return it. We're going to return that. So somewhere in here, down below, we're going to want to return L. All right, so now let's write the guts. Well, we want to walk until we reach the end of either L1 or L2. So our while statement is going to say while the loop counter or the list counter, index counter for L1 is less than the length of L1, right? When it equals the length of L1, then we've used up all of the values in L1. So while I1 less than the length of L1, and while we haven't gotten to the end of I2, so we need an and in here, right? If we get to the end of either one, we're done. With at least any comparisons. We don't have to think about it anymore. We know just copy the end, right? So we're going to go until we run off the end of one of these lists. So we're going to process whichever one has the smallest value, has the smallest, largest value, or however you want to think about it. We're going to process completely. And it's really a simple test. It's just what we did before. If L1 sub I1 is less than, right, if the smallest current value is at the head of L1, well, then we just append that value to the end of L, right? So that becomes the next element of L. And now we have to step down through L1. So we'll just increment our L1 head of the queue counter by 1. If it's not the case, well then the smallest value must have been in L2. So we will just copy paste so you don't have to watch me make mistakes, or at least not the typing mistakes we'll make some other kind of mistakes, probably. Okay? So if not, if the smallest value isn't at the front of L1, then it must be in the front of L2, and we'll just take that value off, append it to our list, and step down through L2 as well. Now when we're done, we've reached the end of one of our lists. So we can just do something like this, L dot extend. And if you look at extend, it just takes all of, it takes a list and extends the L list by the variables in the current list. We could do this with a while loop as well. But for L1, we want to take everything that's left. So from I1 down, right? And if I1 is stepped off the end of the list, this is the empty list. And for I2, we want to do the same. And it doesn't matter which one got empty first, because if one of them's empty, we extend L by nothing, and the other one will kind of fill it up. All right, so that's the merge algorithm. Let's go down and we'll take that out. We'll put the testing in for that. And, so now we should be able to run that. And we don't have the merge sort. I'm not sure we're going to get to the merge sort today. In fact, I'm fairly certain we're not. But that takes these two lists, and you can see that this is the first list, this is the second list, and then this is the sorted list. And you can see we have 2 zeros, we have 2 9s, we have a 9 4, a 9 6, a 15, a 21, a 26, a 35, a 145. This really isn't a very good test, because we really do want to go through and mix up some values. But it's a decent first shot. Let's kind of mix this up a little bit. These have to remain in order, but we can do 6 minus 19. Oh, I can't do minus. 6, 8, 22. So this time we'll make, or 20, we'll make this one fail first. And maybe we want to do a minus 7 here, just to give us a negative number. Right, and we can run this again, and hopefully this will also come out merged in order. Okay, and if you look at this merge algorithm, right, we walk through the entirety of, at most it's L1 plus L2, right? We walk through one of them completely here, we walk through the other one partially, and then whichever one we didn't walk through, we walk through at this time. So this phase takes order of n time in the length it takes order of n time where n is the combined length of L1 plus L2. Okay, so if L1 and L2 are both length 1, this takes time 2. Both 2, it takes times 4, etc. All right, I am not going to Carter, excellent point. In the O notation, I talked about order base 2 because base 2 is what we deal with when we're throwing away half of the list, but the base really doesn't matter. That's why we don't bother specifying it. All right. I am going to go back, and we are going to leave this here. We will pick up with the merge on the Tuesday before Thanksgiving next week. All right. But this is at the basis of the merge sort. This is actually the hard part of merge sort. The rest is just a conceptual leap. So we will walk through that fairly quickly at the start of the lecture, and then we'll see what else we cover. All right. Thank you all. I'm going to stick around again. You guys should go. I kept you 3 minutes long. You're lucky. Normally I keep people about 10 minutes long on this lab or this lecture. But I like you. You're good people.